Okay, so here we're going to work out question 16 and see how you find the center of mass of a centroid given you have those properties in place. And then we have that as the density of what we're looking at. So here they're asking us to find the center of mass. So the first thing that you need to understand is how do you get the center of mass? So this is obviously just going to be the coordinates of the center of mass, and those coordinates are going to be given in terms of x bar and y bar. So these are going to be the coordinates of the center of mass for that particular shape. Now, how do you get the center of mass? So this is basically just going to be that, which is if you're trying to get the x coordinate, so the x coordinate will be equal to the moment of inertia, or the moment about the y-axis, over the total mass m. So this is how you get the moment, the coordinate, the x coordinate of a mass. And then next up, if you're trying to get the y coordinate here, going to be similar, but now it's going to be the moment about the x-axis, and then over the total mass of the system m. So basically, this is what we're going to go with in terms of working out these problems. Okay, so first thing, of course, here that you're seeing is we will need to know how to get the moment about the y-axis, and we'll also need to understand how we get the moment about the x-axis for whatever system we've been given. And then the bottom part there, of course, is just going to be the overall mass of that particular system. And then, of course, bring them together, the coordinates. Once you find x bar and you find y bar together, of course, those are going to give us the coordinate of the center of mass. Now, how do you proceed with this? We're looking for center of mass. Yes, we're looking for center of mass. To find the moment about the y-axis, so here are the formulas that you need. So if you're trying to get the moment, let's say, about the x-axis, so this is going to be the density and then the integral. So of course, in terms of the boundary here, up to you really how you're going to assign this. So for the formula we're going to say from B to A, but basically anything is fair game. And then you have the two functions that you have, f of x, g of x. We'll see where these functions come in, and then divided by 2. And then these will multiply the difference between the two functions. So f of x minus f of g minus g of x. And then with respect to x. And if you're trying to find the moment of inertia about the y-axis, not the moment of inertia, the moment about the y-axis, this is going to be the density. And then the integral, still the same, I'll say from B to A. And then in this case, since this is about the y-axis, this is just going to take, instead of going for this, instead of going for the summation here and then divided by 2, since this is basically about the y-axis, here the value or the expression is just going to be x. And then the x will multiply the difference between the functions. And here, of course, we're going to have f of x minus g of x, and then still dx. So this is if I am keeping it with respect to x. These expressions would change if I decide to go with maybe a dy here, meaning that, of course, these will have to be functions of y. And then this, of course, will have to be a y here as well. A few things would have to change here. So depending on the problem that we're given, we have to be flexible on what we're going to use. So if you're trying to understand where the divided by, why here we get to divide by 2 and here we do not divide by 2, it comes up to where this is. So the moment, of course, it's just the rotation about the x-axis. So how is it going to go there? So in this case, if we are going about it with this function, f of x plus f of g then divided by 2, what I'm basically trying to say here is the way these are given f of x, it means that these are basically y values. I can say that this is maybe y1 and this is y2. So it's like we are adding the value of y at the top and the value of y at the bottom. And then after adding these, dividing them by 2, notice that this is what gives us exactly what this midpoint is. So by adding y, I wrote y1 and y2 and y2. By adding y1 and y2, we're just trying to say that we're just trying to find what this point is going to be. So this is why here you have this expression here. But in the other part, you do not have that expression being presented. The idea there is that here, x is just basically going to come up to where that is. So there's no need for us to say divided by 2 anymore. That is when we are approaching it for this part here. Okay, so I hope you have got how that one is being obtained. Why here we have to divide by 2 and here we do not divide by 2. Again, in CEE, we're going to understand it better on how it goes. So for now, we'll just see how to use these formulas from a mathematical point of view. Any questions up to there? So now I want to use these formulas to obtain what we are looking for. So look at the first problem. In the first problem, we're going to do A16a. We're given two functions here, y is equals to x minus x squared, and then we also have y is equals to minus x. And then we're taking the density as just rho there. So we're assuming that here the density is uniform for these materials. So you'll see most likely that density is going to cancel out. Perhaps that's why in the CEE equation density doesn't show up. The assumption is that you're dealing with a uniform density. Okay, so how do you work out that problem? So for that one, the first thing perhaps you might want to picture the problem. I always feel like having an idea of how the problem looks like kind of helps you work it out. So I'll try to create a rough sketch of my problem. So what is happening here? I have the bottom one here, or I have this one here, which is y is equals to negative x. The equation for y is equals to negative x looks like this. So knowing some of these equations in advance can really be of help, because you would not have to start going through the hassle of plotting them from scratch. Because I know y is equals to negative x as slants downwards like that. Y is equals to positive x would have had to be something like this. But since it's y is equals to negative x, we have that one there. So we can even label it y is equals to negative x. Then the second one there, we have y is equals to negative x minus, not negative x, y is equals to x minus x squared. Now, this one, how does it look like? Of course, with the power 2, I know this is quadratic, meaning it curves at least once. Not at least, it curves once. So how will it curve really? So I have y is equals to x, and then this will be x minus 1, not x minus 1. Y is equals to 1 minus x, like that. So that is how it reduces. When I continue this expression, I want to find the critical points here, or where it will cut the x-axis. So I equate this to 0 to find where it cuts the x-axis. And when I equate it to 0, like this, I find that it cuts the x-axis at x is equals to 0. It also cuts the x-axis when 1 minus x is equals to 0. And at that point, I see that x will be equals to 1. So it cuts the x-axis when x is equals to 1, I'll say here. When x is equals to 0, I'll say there. And when x is equals to 1, I'll say here. So now that I know where it cuts the x-axis at, the next thing I need to understand is, where is it turning? It's quadratic, so I know it's either like this, but of course just at 0 and at 1. So like that, a bit like that. Either it's something like this, or it is something like this. So again, I have to go back to my math and try to remember as much as possible so that I don't waste time with my sketch. So looking at the equation I have, when the x squared term is the one negative, I know the turning point is a maximum, meaning it faces downwards. If the x squared was positive, I would have known that the turning point is a minimum. It would have been opening upwards like that. So just by looking at my expression there, I know to say that here it must have a maximum turning point, so it must be opening to face downwards like that. So this is how my expression looks like. For this calculation, we have no interest in knowing the turning point, so there's no need for us to find where the turning point is. Just this is going to be enough. So I'll just extend my lines so that I also show where they get to meet. So this one, I want this to continue slightly coming downwards like that. And then I also want the blue one to extend. The blue one is easy to extend. I can just get it. Okay, so I have this. And since we are looking for the center of mass of a thin plate covering the region described, so covering the region described by the, so here it's the region bounded by this. So since I'm going for the region bounded by those curves, I need to understand what they close in. They basically, we'll be talking about this region here all the way up to here. So we also need to understand the boundaries where our integrals are going to run from and to. So in this case, it's where the two graphs meet. So how do I find the areas where they meet? Of course, the first one is easy at x is equals to 0 at that point. But to find them, since this is y, just equate them. At what points are they equal? So at what point is x minus x squared equals to minus x? This is what we're trying to work out. So here, of course, x goes to the left. You're going to have x plus x minus x squared is equals to 0. Now you have 2x minus x squared is equals to 0. And finally, factor out x. You don't want to divide by x. That is not, you're going to lose something. You're going to have 2 minus x here is equals to 0. So that from here, for two terms to multiply and give you a 0, it means that either the first term is equals to 0 or the second term must be equals to 0. From the first term, x is 0. The second term, we have x is equals to 2. What this is telling us is that here, these functions, they intersect at x is equals to 0, and the second point of intersection will be at x is equals to 2. So we now have our points of intersection. Now we can move on to get the centroid, or the coordinates of the centroid, of the center of mass. To get the coordinates of the center of mass, according to the formulas we have here, so look at this. In this expression, where you have f of x, so let me get these formulas. Let's try to understand which one goes where. Which one comes out as f of x, which one comes out as g of x. With my sketch in place, it's easy to get them exactly where they're supposed to be. And in this case, f of x must be the function on top. G of x must be the function that is down. When I look at this, f of x is that function in red, and that function in red was the quadratic. So I'll say, in this case, f of x will be the quadratic, and the quadratic was x minus x squared. G of x is the straight line down, and g of x will be equal to negative x. So which is this one. So already here, when finding a moment about the x, what are we going to do there? Already we can see that this part here, f of x minus g of x, f of x, what do we have f of x? We have x squared minus x minus x squared. So let me just do that part. F of x minus g of x, this will be equal to x minus x squared then minus g of x. G of x comes with a negative there, so it's going to be minus x. Notice that this reduces to just, this will be plus, reduces to 2x minus x squared. That is what we're going to have there. So this difference is ending up as just 2x. So this is ending up as 2x minus x squared. But we still have the rest of it. We still need to understand what these are going to be. And then we also, our f of x and g of x, here we already have what these are. Okay, so here we have f of x plus g of x. So what are these going to be? In this case, f of x and g of x, where we're going to get them from? We already have the functions in f of x and g of x. So just add them. This time they're saying add them. So instead of subtracting, here we're going to add them. So if we add, we're going to have x minus x, which is going to give us 0. And then what will remain here is just going to be minus x squared. So that is what we're going to have there, minus x squared, as when I add them here. But remember, we have to add them, then we have to divide by 2. So here we'll have minus x squared divided by 2. So this is what we are going to have here. So now we just have to simplify this. The 2 is also a constant, so I can say the 2 can come out to join the density here. Oh, we also need to know what these are going to be. So when I distribute the x squared, it's going to be minus 2x to the power 3. The x squared and x will give us x to the power 3. This will end up being plus x squared and x squared will give us x to the 4 dx. So that is the integral that we're going to work out. But also need to understand what the limits of integration, what those are going to be. So what are we going to use here? So the limits here, they are just going to be the points where these graphs are intersecting. Okay, so in this case, our functions, our values of x, they are changing from 0 all the way up to 2. So x, in terms of what a and b, what they are, the condition, if you followed what was given in class, the condition is that a is less than or equal to x, which is less or equal to b. So this is how a and b are related. In other words, a is the small one, b is the big one. So here our x will have to be 0, our a, will have to be 0, and our b will have to be 2. Based on that, if we follow this, what are we going to have here? We're going to have rho over 2, and then this is going to be 2 will have to be here, 0 will have to be there, and then this is going to be minus 2x to the power 3 plus x to the power 4, and then dx. This is the integral that we'll have to work out. And of course, this is a basic integral. We have rho or 2 there. Let's integrate. I'll add a 1 to the power 3 there, so that it becomes 4. So this will be 2 over 4, which is 1 over 2. So this will be x to the power 4 over 2. Plus, we'll add 1 to 4, it becomes 5. So this will be x to the power 5, and then we'll divide by the same power. The 5 will be here. This was changing from 2 to 0. And then when we proceed, when we substitute 0, everything just becomes 0. So only look at the negative part, the one because it's the upper minus the lower limit. So we'll have minus, when you substitute the lower limit, it's going to be minus 2 to the power 4 over 2 plus 2 to the power 5 over 5. So this is basically what we're going to have here. So that you have rho over 2. And then here, I can remove the negative, distribute it there. 2 to the power 4. 2 to the power 4, I think that is 16. This will be positive 16 when I multiply the negative inside. Positive 16 divided by 2, that will just be 8. So this will reduce to just 8. Now this will be minus. Here I have 2 to the power 5. 2 to the power 5, that is 32, divided by 5. So of course, if I make any slight error there, feel free to just bring me back. Okay, so just track the negatives, how they're being distributed there. So this is what we are reducing to. I can divide everything by 2 so that I have the 2 here, get rid of it. This will be 4 minus, this will be 16 over 5. So this will be rho 4 minus 3.2. And then this will end up being 3.2 give us 0.8. So this will be 0.8 rho there. So this will be the moment about the x-axis. To now get the coordinate there, since what we found was the moment about the x-axis, mx, observe that we do not use mx to find the x coordinate. We use mx to find the y coordinate. So since we found the expression for mx, we're going to use it to find y bar. So when we come down here, we're now going to say that, okay, the y coordinate of the center of mass will be equal to the moment about the x divided by the overall mass of that section. We already have what mx is. We got it in terms of this as that expression. But for the mass here, we're going to use that relationship for the area density. So we're going to have mass over the area. So here, what will be mass and the area? This will imply that the mass can be seen as the density times the area. So this is what we're going to put here. But again, what is going to be the area? So when we view the area here, you have to see that to get the cross-sectional area, we can still use integrals to picture the area. So again, consider just, let's go to just something general. If you consider an event where, or a case where you have a graph like that, and a graph like this, where this is f of x, the one on top is f of x, and the one below is g of x. If you wanted to get the area enclosed by these two functions, what you would do, if you're using the differential approach, you'd pick a small differential section. You can go for rectangular like that, and we'll say that this has a thickness in terms of x. That thickness, we can take it as dx. And then, you know, to say when getting the area of something rectangular like this, you have to multiply the length and the breadth. So the breadth is going to come out as that thickness. The length will have to be from the bottom all the way up to the top. Again, observe that here, when getting the length, you end up with the upper function minus the lower function. So to get the area of that differential section, to get that area, dA, notice that you still reduce to the length, which is f of x minus g of x, but multiplying the thickness there, which is dx. So that now the area we want, A, will just be equal to the integral of f of x minus g of x dx. This is what is going to give us the area. So observe that even this formula we had here, we could have looked at, not this one here. We could have looked at it in terms of presenting M also in terms of density times area. But if we did density times area, notice that the density that would come from M, I'm going for this one, My, and My would be here. Notice that the density would cancel with the density that will come from the mass. Because even as you see on the one we are currently working on, the expression for the area has just come out as, so our mass now has reduced to density and our area has reduced to an integral, f of x minus g of x, multiplying dx. So when we plug that in our expression for y bar, the top came out as 0.8 times density. But the bottom is the mass, the overall mass. But the overall mass we've just seen, it also comes with density there. And then the integral in place, f of x, the upper function, minus the lower function, and then dx. The density here would cancel the density on top. So again, this is like I keep emphasizing, say, in the CEE approach, or the method that we use in CEE, density will not be present in the formulas because density cancels out. In the CEE formulas, this formula for y bar will not be given as mx over m. Instead, it will be given as a simplified version where this is expressed as the y coordinate of that differential section. Since this is for an area, dA over the integral of dA. So notice that it's like they are just presenting this. They're saying that density has already cancelled out already. So this is the relation between when you look at it from a math point of view and when you look at it from a CEE point of view. In CEE, I feel it's more easy to understand than the way it is presented in a mathematical, from a mathematical aspect. So what I would encourage you guys is try to look at it briefly from CEE. That will give you a deeper understanding of these concepts. Okay, all in all, that has cancelled out. The numerator has just remained as 0.8. Now let's find what that integral is. The difference between fx minus g, I think we obtained that already. Fx minus g of x, where did we get that? Okay, so when we did plus, it ended up just remaining as this. When we did okay, I think I changed it. When we do minus, it's x squared minus x. This ends up x plus x minus x squared. This will be 2x minus x squared. So this becomes the difference there, 2x minus x squared. So we're now just going for the integral of 2x minus x squared, and then dx. So in this case, when we integrate here, again, don't forget, it's still over the same region, meaning in the same margins that we're evaluating. And even when you look at our formula, okay, so for the area here, we don't have the preset movement, say it's from A to B or what, but just be careful. When you plug in your limits here, if it gives you a negative, swap them. So when I say from A to B, if I find that the area I get here is going to be negative, I'll just do from B to A, because I know to say that area is not supposed to be positive. But let's try to follow suit. Let's go B to A and see what we're going to get here. So if we do it like this, first the key thing is integrate correctly. This is going to be 2 over 2 x to the power 2. This will be 0.8 over, this will be 2 over 2, so just remain this to the power 2, minus, this will now be x to the power 3 over 3, and then the limits, since I'm saying b to a, so this is going to be 2 here, and a 0 there. So again, just focusing on this, if it gives me a negative, then I'll have to swap those, because area, remember that is giving me the area, not the coordinate. The coordinate can be negative, meaning it's okay if the negative is coming from the top, but this is supposed to give me the area, not the area, the mass. This is supposed to give me the mass, so I don't expect my mass to be negative here. So when I just focus on the denominator there, what do I get? When it is 0, of course, everything will just be 0. When it is negative, I'll have this. I'm putting a 2 there. This is a 2 squared, that will be 4. And then this will be minus, that is going to be 8 there, 8 over 3. Already here, I see that this is going to give me a negative value, because this, of course, is going to be a positive term. This is going to give me a negative term. So I know to say I don't want to play with my limit from B to A. Instead, here we're going to follow the normal standard from A to B. This will end up giving us a positive mass, which is what we want. From A to B, meaning it's from 0 to 2. When we do it like this, it now means that when we substitute 2, that is what survives the upper limit. So this is going to be 2 squared minus 2 to the power 3 over 3. And then minus, when you substitute the lower limit, we just get 0 here. This will now be 4 minus 2 to the power 3, that is 8 over 3. So when we simplify this expression, so present it as a single fraction, over 3, this will be 12 minus 8. This will end up being the difference there, 4 over 3. So this is ending up giving us 4 over 3. Yes, 4 over 3. So we have obtained what, I just focused on what the denominator, that integral, is going to be. So now my y bar is now 0.8 over 4 over 3. So this will just be 3 times 0.8 over 4. So this is what we're going to have there. We can simplify it further. That's 3 by 0.08. So when you simplify this, we get y bar being equals to 0.6, whatever the units are. And this is just a coordinate. So even if we can, to be sure, if it is meters, it will get meters, centimeters to get centimeters. So in the same way that we approached this one, you're now supposed to do the same thing to find x bar. To find x bar, we sought to say that you need the moment about the y over the same m. The m is the same that we got in the earlier approach. So it will still be the same expression. You can still bring it with the density, since my will come with density. But you have to know that density will come and cancel. The m will remain as the same integral we obtained in the previous case. And that integral reduced to just 4 over 3. So that will still be the same, since it's the same shape. Its overall mass is expected to be the same here. So basically, this is what you do. The only work that you have to do is to get my here, the moment about the y-axis. So here I can say that in the denominator, it will still be rho multiplying 4 over 3. And then bring what that is going to be. It will also come with a density that will end up cancelling with this. And then it will reduce to just a shape, the number there. It's the same trick here for all the others. So what I'll ask you guys to do is, can you try to work out the other 3 there? Let me know if you find any trouble. Tomorrow we're still going to have more class. If you have any challenges here, we can pick one of them to also do, the one that might trouble you. Otherwise, for tomorrow, we can come and focus on getting the moment of inertia now, I. So we'll pick one of those examples from 17 to see how we get the moment of inertia. Now, guys, we'll discuss in the group if you have any challenges. Have a good night. We'll share the PDF in the group as well.